Okay. Need to confirm if we are live. And it seems that we are. Great, and things are working, which is nice. Okay. So I am definitely aware of the fact that I'm early right now. Wait, need to sort of mute myself on YouTube there. Okay, so we are early. I'm just going to grab myself a drink right now, and we'll get started in a bit. But I just want to always start a little bit early to confirm that the doodling works, and that seems to be the case as well, so that's good. Yeah, so we're gonna start talking about embeddings in a bit. If you give me like another 4 minutes to get my drink, we should all be good. So be back in a bit. Okay. Almost ready to start. Let me just check a few things. I've notified people on Twitter, so that's good. Notified people on LinkedIn, if I'm not mistaken, so that looks good. Yeah, okay, so we can just wait for like one more moment, and then we're gonna go ahead and get started. I'm setting up a window over here so I can see the stream and also some of the comments that come in, and that will be nice because then if people ask questions, I'm able to answer. Right, so open up that live link. That looks good. Good, 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 good. Sweet. So if people could let me know if they are in, like I do want to wait for a moment to see if people are actually in before I actually, go ahead and get started. But if people could just let me know that they're able to see me and connect, that'd be grand. I see some people watching now, so that definitely looks good. But if people want to say hi, that will be helpful at this point. Just give it like 1 or 2 more minutes. Oops. Yeah, so kind of the annoying thing this week is that I'm at a standing desk right now, and the microphone is attached to my desk, so you're gonna hear a little bit of extra sounds when I'm typing. Unfortunately, I'm gonna do my best to sort of keep it on the down low, but it does seem that we are at starting time, and I do see that 3 people are tuning in, so this is good enough for me to go ahead and get started. But what I thought might be fun for this week is to do stuff with embeddings. There's a bit of an interesting story here. So a few years ago, when I worked at Rasa, I was definitely playing around with like text embeddings, let's say. And back then, I wanted to have a way to just get that into scikit-learn real quick. Eventually, that led me to write this one package called Embetter. I thought the name was relatively clever. But this package basically integrates a whole bunch of what I think are relatively useful embeddings. So there's some embeddings for text. There are some embeddings for images. There are some multimodal embeddings, some embeddings for providers. We've got some stuff in here. And the point is to just make it easy for scikit-learn users to go ahead and use these embeddings as well. So the way that it works, just from reading the docs, is you can pip install Embetter, and then you are able to import tools that you can use inside of a scikit-learn pipeline. And you know, the docs have some examples. Like this is just from the GitHub README. I've got some like the sentence transformer is like one of the more popular text embedding packages out there, and I've got support for that. There's also one that I thought was kind of nice from my previous employer called sense2vec. I've got support for that. And there's also some word embeddings. I thought byte pair embeddings were kind of nice, so that's also something that's been added. But besides that, there are also some image models, like Clip. And what I thought would be kind of fun today is to sort of explore this library and explore some of these tools. And this will allow me to sort of demonstrate some use cases for these embeddings inside of scikit-learn. And it would also be an opportunity for people to ask questions if they have any. Hello, Luke. Nice of you to join in. So as a quick demo, what I've just done is I've got this notebook over here. And this notebook, let's make this a bit bigger. Save the screen real estate a bit. But one thing that's kind of nice about the setup over here is that I have a CSV file with lots of texts. That's sort of the starting point. These are texts from a data set called Clink. And if I'm not mistaken, the whole point of this data set is that there are 150 classes of something you could type into a chatbot. This data set is relatively dated for today's standards, but the original goal of this data set was to have lots of topics, 150 of them, and also have one out of scope topic. So there are a couple of these texts that have nothing to do with any of the 150 classes. And the original goal of this data set was to identify these out of scope topics based on this text. What's interesting about this data set for me, though, is that this is a data set with 150 topics that are nicely clustered together, which makes this data set kind of nice for demonstration purposes. So you could look at this and say this is kind of like a text classification data set in a way. It's just that we have lots of different labels, and we usually are dealing with like a one-sentence text, not like long paragraphs or anything, just a long sentence thing. Okay, so that's all well and good. Maybe you want to do something with embeddings now, because what we have at our disposal are these pre-trained language models like BERT and like a whole zoo of them. And we can ask these pre-trained models to accept the text and to then turn it into some sort of vector or some sort of numeric representation. That vector is something that you can then use for whatever purpose, but for scikit-learn reasons, you can use that vector as input. Just like in scikit-learn, we have a count vectorizer that can turn text into something numeric. Nothing is really stopping us from taking text and putting it in the neural network to give our algorithms a numeric representation. So, as a very quick demo, what I've got here is zoom in once. I've got this pipeline. I'm giving this pipeline a sentence encoder. For all intents and purposes, this sentence encoder, maybe you should not glance over that. The sentence encoder is something that I'm importing from the Embetter module, so you can see that I'm definitely doing that over here. But the sentence encoder, if I just have a quick look at the implementation, there are lots of different models to pick from, but this is effectively a scikit-learn component. So if I were to just render it like this, you can see that it renders just like any other scikit-learn pipeline, because under the hood, I am using scikit-learn's base construction components to sort of make this be a proper scikit-learn element. And that is something that we can also confirm from just looking at this pipeline. This pipeline has a sentence encoder in it. This is really just like any other scikit-learn component. This component expects a list of texts to go in, and then it can emit an array. So just as a quick demo, and this will take a small while, I am giving it this array of texts. This is the data frame that I started with, and I'm taking the text column. And then after a while, this could be a small while, like it's not a super small data set. It shouldn't take forever, but while this is running, like after a while, we should see that a NumPy array comes out. This is something I could have ran beforehand, but let's just wait for a bit. There we go. So this is a NumPy array that's coming out. I'm using the base model from the sentence encoder. That's the base model for sentence transformers. And that has a neural network that outputs a array of size 384. So this array over here has lots of columns with lots of numbers in it. But it has about 20,000 or so rows. And if I could check that with the shape of the data frame, that makes sense because I have one of these arrays for every row in my data frame. So each text went in, each text gives me an array out, and that gives me this large array with lots and lots of columns, but it's still a one-to-one mapping. One text, one embedding array, so to say. So I was thinking, like, what would be a fun way to demo this? Because one thing that we're actually looking at here is if I just have a look at the top 5, let's say, arrays, and if I have a look at the top 5 texts, there is a mapping from this text to this array. And you could wonder, well, what's so special about that array of numbers? Because you can also just do NP random, right? If you want to get an array of numbers for a text, there's also a way to go about it. But the thinking here is that this representation, this sequence of numbers, this has something of a similarity with other sequences of numbers. And the hope and thinking is that we have a pre-trained model that is pretty good at figuring out if two sentences are similar. The way that these things get trained, by the way, is that there are these big data sets where you have you've basically got two sentence pairs, and then annotators say, well, that those two sentences are similar or they're not. There are these data sets that exist for this. And a lot of these models are trained for this particular task, like base similarity, can we go ahead and predict that? So in theory, right, you would hope that a real-life sentence, if that's similar to another real-life sentence, that the numerical arrays that come out are also close to each other, that they're mathematically similar. And to sort of explore and confirm that, what I've got over here is just a little bit of code to sort of demonstrate this. I'll go over it bit by bit, but I've got a sentence over here. Can people actually... I need to... hang on. I need to make sure that the screen capture is actually able to show that. It seems frozen again. Let me fix that. Screen capture. That's it. Okay again. So okay, we had a small frozen moment, but I think we can see this again now. So what I've got here in this code is I am importing the pairwise distance module from scikit-learn. And what I'm going to do is I'm going to embed a single sentence. So I have that pipeline that I started with. The pipeline that I started with is going to receive a single sentence as input. And that means that I have a sentence embedding that kind of comes out. So if I were to run this, this one sentence embedding that I've got over here, this is an array, a single one. And that single array belongs to this sentence that I've got over here. So if I have the sentence, play me some fun music, some array belongs to that, and that is something that I'm calculating here. So this embedding belongs to this sentence, so to say. Okay, so far so good. But what can I then do? Well, since this is an embedding, I could go ahead and compare this array with all the arrays that I have from my original data set. And to help me with this, scikit-learn actually offers this one like pretty neat utility. There's this pairwise distances function. And what it basically allows you to do, I'm just going to grab the docs for that, is you're able to say, well, I've got one array or a matrix X, and I've got another Y, and I would just like to calculate all the distances between them. So every row in X and every row in Y is going to be compared with one another. And not only that, but I'm also able to say, well, based on what metric. So I can say I want the distance between 2 points, or maybe the angle between 2 points. There's lots of these metrics that I could go ahead and pick. But this pairwise distances function is just something I've always found kind of useful to have around. And this is like one of the things that scikit-learn actually offers. And there's a couple of internal methods, I think in the k-nearest neighbor department, where this is also being used in a couple of spots. What you can even do if you've got like huge arrays, you are even able to parallelize that if you'd like. I've never really been able to use this in a way that things become quicker because there's some overhead involved, but it's nice that it's around. But anyway, this pairwise distances function is pretty dang useful. And what I'm saying here is, okay, let's compare this one embedding to all the embeddings that I started out with. All the embeddings that I have in my Clink data set. And let's also compare using cosine distance. Cosine distance means the angle between two vectors. That's a metric people like to use. Then when I run this dists variable contains lots and lots of distances. So this is the cosine distance between the first array and the sentence array, the second one, etc. And what I'm interested in is the most similar 10 items. And to do that, there's just this NumPy function called argpartition that is very helpful for that. And that gives me the indices that should be the most similar. So I've got my NumPy array here with items that should be similar according to the cosine distance. And that is something I can use as a predicate to fetch the rows of interest from my pandas data frame. And what's kind of cool about this is I'm able to just type in the query. So maybe something like roll some dice. I think that's also a topic in this data set. Yeah. And effectively what I'm doing here is neural search, which I thought was kind of like a cute and interesting demo. So I'm going to start drawing to explain all the steps that we're doing here, but let's just move things around a little bit. But what's really happening under the hood here is that I have some texts, like a large set of texts, and then I am embedding those. And that kind of gives me a data set or a database of vectors, I guess. And what I can then do kind of as a query, that's a single sentence, I can again turn that into some, let's say, n-dimensional array. And I can then compare that to all the vectors that I've got, and then I can say, well, just give me the stuff that is similar. And as an effect, like something we can confirm here, it really does feel like we're doing something like a search engine, but we're not really doing anything with text at all. We have a machine learning model that can turn a text into a vector, but we're not building a search index or anything formal like that. We are really just comparing these vectors. And apparently there's something about this embedding internally that is learned to represent the data in some way, that if I use cosine distance as a metric for my query, that I'm then actually able to grab stuff that is similar. And I kind of get that for free. I didn't have to train on a huge data set. The pre-trained model has already done that. So the fact that I'm able to confirm, that similarity kind of comes out the box, that is stuff that we can go ahead and use. That is something that's kind of useful. And just to give like, whoops, don't touch the boomstick. And just to give like a a few more, like, I guess, interesting examples. Like, another thing I could go ahead and do is, I don't know, maybe with something with credit cards, I think, maybe. Yeah, so there's a couple of banking topics in this thing. Lost my banking card. Yeah. So this one is pretty interesting too. Like, I can describe here that I've lost my banking card, and here it's saying I need to replace my lost card. So, you know, it's similar words are definitely making an appearance here. Maybe what's a different word for card? I no longer have my royalty. Yeah, I guess card is required maybe, but yeah, like something. So it's able to sort of understand that the topic that I'm interested in is the card, and it's able to also retrieve items from my database that have the topic card in it. Like that word makes an appearance, and there's something about that that's making this trick kind of work. So, you know, this is kind of a cool demo. If you're interested in retrieval, this is definitely kind of nice and useful. But so far, technically, you didn't need the scikit-learn stuff so much. Like, the only real integration with scikit-learn that you're seeing here is this pairwise distances thing. Like, I'm not doing anything with the fact that this Embetter library is able to do something for scikit-learn with these embeddings. So, to maybe help out with that, I've got this other demo that I would like to move towards. But before we get there, I think what I want to do is also explain like a weakness of these embedding models, because this is something that's a little bit under-discussed, I think. So just as a thought experiment, and definitely feel free to like send me what you think should happen here. But just as a thought experiment, right? Like, let's say I've got these three sentences. So I've got the sentence, I love dogs. I've got this other sentence called I hate dogs, and I've got this other sentence called I love Python. Again, as a thought experiment, let's say we're going to embed this. Each sentence is going to be turned into a sentence, and then the question is, like, what would you expect? Like, which of those embeddings will be very similar? Would I love dogs be very similar to I hate dogs? Or would I love dogs be more similar to I love Python? And what I hope you understand from this one simple example, right, is that it's actually kind of tricky to predict ahead of time because it depends on what the model has been trained on. I could argue that for the first two sentences, right, it is both about emotion and it is both about dogs. So that could be a reason why those two sentences are similar. However, at the same time, both of these sentences do carry a somewhat opposite meaning, so that could be a very strong reason to consider that these two sentences are dissimilar. You could argue that maybe I love dogs is very similar to I love Python, and that could be true in a way, but it does depend a little bit on the context, because Python could be a programming language, not an animal. And you could also argue, well, the fact that you like a mammal, like, why would you love a snake at the same time? Should that even be similar? Like, what does similarity actually mean here? And in the case of, you know, metrics and math, it's relatively easy. We can declare two arrays similar based on whatever distance metric that we can come up with. But to what extent that actually translates into actual meaning of words and sentences, that's kind of a different topic. And a lot of that depends basically on the training data that these models have been trained on. So just for demo purposes, I thought that was actually kind of a cute thing to show as well. We are looking at the cosine distance here. So basically smaller means better. Oh, actually, I'm not sure if this is cosine distance, actually. This might be Euclidean. Let's just double check that. So metric equals cosine. Let's just do that for good measure. Yes, okay, so we were looking at Euclidean distance, which is distance between 2 points. This is the angle between 2 points. But we get a very similar conclusion, because one thing we can see is that the distance from the first row to the second one, that will be this number, that is much smaller than all the other ones. So it seems that according to this embedding model, right, I love dogs and I hate dogs are very similar sentences. Now, again, I think it does make sense if you consider like what's being expressed here. Like we could argue the main topic is dogs in both sentences and a emotion is being conveyed. But I do like examples like this because you should always remember that we're still dealing with statistical models. They might not exactly match your expectation from reality. That's something to always keep in the back of your mind. This also kind of depends on what embedding model you pick. I can imagine maybe if you have a much larger embedding model, like maybe you have the model from OpenAI or something, then it might be able to capture some of this stuff a bit better. But you shouldn't expect some of this behavior out of the box for everything. There's still nuance, and language is still a tricky topic. But yeah, I think some people got it right. So I love dogs is similar to... So this was what I was hoping for. So Jonathan is saying that Jonathan would have expected that I love dogs is more similar to I love Python. And that's kind of just not the case in this particular case. But I do hope the explanation about emotion and word usage carries enough evidence for you to sort of consider this could also be valid. Again, it depends a lot on the embedding model that you're using, but this is like something that's always good to keep in the back of your mind. Okay. Still, we were moving towards scikit-learn models, and we weren't really doing that just yet. But I hope that this was still like an interesting introduction. Like we have something of similarity. The similarity should not be taken at face value, should not be taken super serious. But there does seem to be something about the similarity. So how about this? How about I use a k-nearest neighbor classifier? So I'm just going to make a pipeline, and the only thing that this pipeline is going to do is this pipeline is going to embed whatever text goes in, and then I'm going to use k-nearest neighbors. And the thinking here is that suppose in high dimensional space, and I'm just going to pretend like my embeddings only have 2 dimensions, but you could argue that I've got one point in high dimensional space where, I don't know, I would like that point to be associated with something that sounds very positive, and I've got something else that I would like to get associated with something that's very negative. So I could take like a very positive sounding sentence, grab that embedding, take a very negative sounding sentence, grab that embedding, and then these 2 points exist somewhere. What I could then theoretically do is whenever a new text comes in, I can just check, well, is that text closer to the positive embedding or is it closer to the negative embedding? And if it's closer to positive, let's just label it positive. Let's just have that be the classifier. And the hope here is that because we've got an embedding model that's seen so much data already, that's already been, that should theoretically be okay at detecting whether or not 2 sentences are similar. That could theoretically also mean that I can construct a machine learning model using just 2 data points, namely one for the positive example and one for the negative example. There are lots of nuances to this, right? But this is kind of the idea of zero-shot learning as well. Like with few-shot, I guess I should say. With as few examples as possible, can we maybe leverage embeddings or something pre-trained to still make a prediction that's relatively reasonable? Here's the pipeline that I made. It's not super fancy, but it basically clicks together the sentence encoder that I got with a k-nearest neighbor classifier. And I'm saying one neighbor is enough. So just take the nearest neighbor and have that determine which class you belong to. And I've got a sentence here. I am super positive I am. And I've got another sentence here. I hate everything, boo and hiss. Somewhat silly examples, I do agree. But I could say, well, I'm building a positivity detector here. Let's associate 1 positive label for this one, and let's associate 0 negative label for this one. These are 2 examples. I'm going to be embedding first, then I'm going to apply my k-nearest neighbor, as I said before. This thing is now trained, and again, if I now give it a sentence like I am happy, then that sentence is going to get encoded first, and then it's going to be compared to what I've got in my k-nearest classifier. So, let's run that again. So I am happy gets correctly classified. I could do something like I am super happy, that gets classified as well. I'm sad maybe would also be a good one to check. I am unhappy. It's not doing perfect. I hate, well, I dislike things. Okay, so we're also able to detect something is a little bit negative. So okay, this isn't necessarily going to be a perfect classifier, but the thought experiment here is that by using an embedding, I am able to get something that's not unreasonable here, because note, the word dislike does not appear in my training data whatsoever, but because I have embeddings, I'm still able to make a somewhat reasonable classification at times. And the thinking here is that this could be a time saver, especially if you come from the realm of data annotation, where sometimes you just want to have a model that's maybe not amazing, but the model can help you find subsets of your data to maybe label first. And for that, this is like a very awesome field, so to say. One thing that I am going to do now, actually as a small little reminder, is I think, yeah, I still need to give it like a proper metric. So I think I'm able to give it a cosine distance here. Yeah, so that should already make it like a little bit better. Something like I am happy. Yeah, okay, that's positive. Might be another one. I am extremely optimistic, let's say. Okay, I'm extremely pessimistic. Okay, so it's still definitely not perfect. It would probably be better if you had like lots of examples as opposed to just this. I guess like one thing that I would also be good to show. Yeah, so I'm happy, it gets that right. If I say I'm not happy, it doesn't necessarily get that right. So again, like I don't want to emphasize that these models are going to be perfect or anything, right? Like it's something to always keep in the back of your mind, especially when you do something subtle like negation. That's something these embedding models are notoriously having a bad time with. But again, just as a demo, I do think it's kind of cool that from the scikit-learn perspective, if you wanted to make a few-shot learner, right, that's actually not too hard. Like we can just grab a sentence encoder, chug that into the scikit-learn pipeline, and this already kind of does it, you know, not in the worst way. There's actually a thing that comes to mind now as I show you folks this. So what I would like to do is give you like one more quick demo with this particular pipeline before moving on to doing, let's say, image stuff. But this will also be a good time, like if people have questions, like prepare them in a bit, because after this quick demo I will have like, I'll give the floor to like some questions. But like one thing with the k-nearest neighbor classifier right now, right? So if I were to do predict Probabl, that is to say we're gonna want to get some probability like values out of this thing as well. Like if I run this, then right now, if I were to type I am sad, let's say, or what was it? I hate stuff. Okay, then the label flips. But you'll notice that I only get 0 and 1s out. Like the k-nearest neighbor algorithm really only has access to one and only one neighbor. So that means that I can only expect 0 or 1 classification probabilities coming out of this thing. But the k-nearest classifier actually has a setting for that too, in case that's interesting. Because what I can also say is, I think it's this weights parameter. It says it has to be uniform. So right now, like one neighbor is equal to like one distance point. But I think if I change weights to distance, yeah, there we go, then the actual distance to the point will also be taken into account. What was the parameter again? It was weights. Weights equals distance. So to maybe explain that subtle difference, right? Like if I've got like a two-dimensional place here, and like this is the positive label and this is the negative one. Before, I could be, let's say, over here, and I would be closest to the positive label, and that would always yield a probability of 1. That also means that if I'm just over the border here and just slightly closer to positive, I would also get a predict Probl of 1, because the distance is really not being taken into account. by setting weights is equal to distance, this will be taken into account. So if I'm not mistaken, I can rerun this now. Have I made a mistake here? I sort of could use more. Huh, I think I've still got a mistake there. I need to dive into this one. I would have expected. Oh wait, it might be due to cosine distance actually. Let's go for Euclidean. It might be related to that. Don't know 100% for sure. Okay. I need to dive into this one. This might... I would be I would be surprised, but this might actually be a small bug. Or at least it's going really against my intuition here. So if I read the docs, what does it say? Callable or none. If it's distance, weigh points by the inverse of their distance. In this case, closer neighbors of a query point will have a greater influence than neighbor. Oh, okay. Right. Okay, so I misinterpreted. I thought the distance was going to be taken into account. And it is, but it's going to still weigh on each neighbor. It's not going to, if you only have one neighbor, look at the actual distance. It's weighing each and every single neighbor separately. Okay, so this won't work. Okay, a bit of a shame. I was hoping it would. But I guess like another thing I could also go ahead and do actually, now that I think of it, like theoretically, right? From scikit-learn linear model import, let's go just for logistic regression. I mean, nothing is stopping me from using another algorithm, maybe like this. And if I were to scroll down now, mouse cursor, yeah, then I do get like probability values out. So I could now maybe do something like I dislike this. Okay, then we get an impression of whether or not the model is actually super sure or not. Another thing that comes to mind is I am positive, right? I am not positive. Yeah, it's barely. So I think this is pretty interesting. Like, notice how the word not barely causes a difference in the Probabl values. So we've got like 0.57 at the end. That gets turned into 7.56 maybe, right? So it's, yeah, okay. So, okay. Hopefully this is a fun demo. I do want to emphasize, it is very cool as a demo that you can make a model out of just 2 data points. And if you're really just getting started and you want to find subsets, I do think this is an interesting way of going about it. That said, though, we are only using 2 data points. And even though we're using an embedding model, your mileage might definitely still vary. So it's like, fair to keep in the back of your mind. There's some other demos I was thinking of to do as well, but maybe this would be a good time to go for questions. I think Luke is asking a question. Would this pipeline get better and better during the course of labeling? The 2 clusters, positive and negative, would get more and more evidence and better defined in the metric space. The short answer is yes, but a caveat. So again, let's do the mildly unrealistic thing and actually pretend that we're dealing with 2 dimensions here, right? So one question could be like, right now I've just got 2 data points, right? Like one for the positive and one for the negative. So one thing that you could get if you're going to train a model on this is that it's really only able to sort of say, well, you're on that side or on this side of the line, let's say. But then hopefully maybe you're going to do some more labeling, right? And I'm just going to do X's for the positive. And then I'm going to do circles for the negative. And if you were doing logistic regression, like the hope is kind of that the separating line would maybe be in a slightly different plane and doing a slightly better job at making predictions. That's something that could be happening here. And this is what more labels would typically give you. Like the hope is that this is going to help your algorithm. That said, we should remember that the embedding model also has a role to play here. So we've got this sentence encoder, right? And that sentence encoder is basically the thing that says, well, this one sentence, when it's encoded, it needs to be over here. So theoretically, you should also keep in the back of your mind that if there's something up with this embedding model that's not necessarily going to be useful for our classification purpose, maybe there's some bias in there, right, or something like that. I mean, there is a limit to what labels can do there at some point as well. There might be a good reason to throw away this embedding model at some point and start from scratch. That's something that could be the case. So it's not necessarily the case that more and more data for always and forever are going to solve your problems. There are still modeling decisions that can help out as well. This is a small caveat. In general, more data, always better, definitely good. But there are these caveats to also keep in the back of your mind. I am a big fan of labeling though, especially if you do this with a group. Label with the group, make sure that people agree, do some iterations on that. That's all good stuff. But I don't want to suggest that more data will always and forever to infinity cause improvements. There are subtle things to keep in the back of your mind there as well. So Magda is asking a question, which is a pretty good one. So in this particular case, right, I've got my sentence encoder over here. And the sentence encoder is really just getting a list of texts, which is what it would expect, which is what it expects. But now the question is what do you do when you have a data frame? Because in your data frame, you might have one column with text, and I don't know, you've got this other column with a category, maybe another column with a category, and you might want to build a elaborate pipeline for this, and you would want to make sure that this one text column gets passed onto this sentence encoder, because we're dealing with a data frame here. So in that particular case, there's actually a tool inside of Embetter called a column grabber, which is subtly different from tools in scikit-learn. I'll explain to you what it does in a bit. But one thing I could do, for example, is I could have a column grabber over here. I could give it the column name text, and then in this case, if I had a data frame with a column called text, then this column grabber would make sure that that column is selected and everything else is ignored, and then this gets passed as a list down to the sentence encoder. So if you are dealing with a data frame where one column needs to be encoded with a sentence encoder, this is the way you would do it. Now, this is subtly, very, very subtly, different than some of the other tools out there. And the reason is that the sentence encoder really wants to have a list of texts. This is kind of the thing it really wants to have. What it doesn't want to have is a data frame with two columns. What it also doesn't want to have is a series object from pandas. That's also something that it doesn't like to deal with sometimes. So if you were to look at scrub to the select calls class that has, if I'm not mistaken, you can give it a list of column names. But here, a data frame will go in, and also a data frame will go out. And again, sentence encoder really likes to have a list. That's just the implementation. That's an implementation thing. There's no way really around that. So that's why I added this column grabber to this library as well. It's just so you can say, hey, I want a column grab. Just grab that one column. And what comes out of this is not a data frame, but this is a list of texts. That's kind of the plan and the hope with that guy. It's a subtle difference, but again, the main thing that's important to know is nothing is stopping you from using it. You may just want to use this component. You can learn more information in the docs about this. There are other grabbing methods as well, by the way, but this is how I solve it for data frames. I also need to double check. I'm not sure if this is supporting just pandas or maybe also polars. I would need to double check that. But this is the story here, at least. Right. So hopefully that was enough explanation to also answer your follow-up question. There's a subtle difference between select call and the compose stuff inside of scikit-learn. But I think we are running out of questions at this point, so that means I can move on to the next demo. So I hope that this was clear, and I hope that people appreciate, there's cool stuff that you could do with this. There's one extra, I think just nice little demo that's worth to do. So one thing that I've also made a while ago is a library called ClueStar. The hope of the library is just to give you a simple function to make this one chart that's kind of useful. So it's clustering and finding the stars in your cluster. That's kind of the name there. But this library has a function called plot text. And the way that it works is you're able to give me an array with 2 columns and some texts. And then what you're able to do is in that two-dimensional space, you can make a selection, and then on the right over here, you can see the text that I've selected, and on the left, you can see the 2D plot. And in particular, what you're looking at here is you're looking at something that's 2-dimensional. And you might think, well, hang on, those embeddings, those are like 380 dimensional or something, so what's happening here? And what I'm doing is I'm using another library called UMap that is really good at taking something that's high dimensional and turning that into a 2-dimensional representation such that local information is kept. This is a bit of a rabbit hole that I don't want to exactly dive into now, but in a hand-wavy, big picture idea, you have this thing called PCA that can reduce dimensions, and PCA is really good at keeping global information, but as it shrinks your data set down, it sacrifices the local information a bit. And UMap is the other way around. UMap will throw away the global information just to preserve the local information. Lots of interesting math happening there under the hood, by the way. But the main thing that is going to be interesting for us is that this gives us a 2-dimensional plot where clusters just kind of appear. And it's partially UMap doing its thing, but it's also partially the embeddings. And one thing that I think is just always particularly fun when you have a new data set and when you do this is you can always kind of play the game of, well, what cluster is this? So again, text, big embedding, 2D representation, plot that, and then I get stuff like this. So how often should my tires be changed? That's something I can read from this. And if I go here, this is also about tires. This is about socket converters, plug converters as they're traveling around places. This is a date for mechanics, like finding a date to get a car serviced. You can very clearly see this is paid time off. There's also a sentence about push-ups here, by the way. So these clusters aren't necessarily going to be perfect, but they are pretty clear clusters. And again, I should also emphasize that the Clink dataset in particular has very distinct topics. So it's also not a huge surprise that we see these clusters, but it's an interesting effect. And it's a fun demo to do on your own text datasets if you've not done this before. And again, I hope you could, from like a distance, you can also appreciate that Vincent has a background in data annotation. And if you're doing labeling, this sort of stuff is also pretty useful. Like it's kind of a nice way to, at a glance, get an overview of all these different topics that are in your dataset. So, okay, I think this is good enough about text. We'll have another question round in a bit, and if people still have questions, like totally go for it. But like as far as demos go, with stuff that you can do with text embeddings, as well as like how would you do pipeline stuff with scikit-learn, I do think that this is sufficient. The next thing that I wanted to do really was do something that's kind of similar, but maybe focus on images. Because so far we've been doing stuff with text, but from a conceptual level, there's no reason we couldn't do this for images as well. I'm going to repeat a few points that I made in one of the videos about a very similar topic, but let me just get some white space over here so I have an area where I can draw. There we go. But from the perspective of a scikit-learn pipeline, the main thing that we care about is that we have some sort of machine learning algorithm at the end over here, like let's say logistic regression or what have you, right? And we need some sort of an array that kind of goes in there. It needs to be n-dimensional, but it can't be text and it can't be pixels either. So that means that before this, I need to have some sort of model that can take an image, if we're going to do image classification, and can then turn that into an n-dimensional array. Now, turns out there are these embedding models for that as well, and there's quite a few. The only thing that this pipeline needs, of course, is we have to discuss like what is an image in this case. An image for most of these pipelines is usually an object from the Python image library, which is a great library, by the way. But that kind of an object is not something you can just load from disk. So Embetter also has a component that can turn text, that is to say a path description, into a Python image object. So this would be the pipeline that you would have to build. You would first have to take a string that represents a path, turn that into an image, and after that, that can be turned into an array, because the embedding models, they know how to deal with these image objects. They don't necessarily know how to deal with text in general. So that means that you will have to have images locally on disk, of course. We cannot just fetch them. Like, we could theoretically fetch them from the internet, but it'd be like a big bother. But this is the way you would construct pipelines for image classification inside a scikit-learn using Embetter. This would be like the name of the game. We offer like lots of different embedding models, but one thing I do kind of recommend you just have a look at is this one model called Clip. And that's because Clip is just kind of an interesting model if you think about it. The way that it was trained, and I'm being very hand-wavy here, but the way that it was trained on pairs of images and texts. And the image has a pipeline where it gets, embedded, feed-forward layers, what have you. And the same thing happens to text here, slightly different architecture. But you can imagine that there's an embedding over here. There's another embedding over here. And then basically what's the data set that they trained on is, again, like similarity, yes, no. Does this text describe this image? And you can kind of imagine if you were to do that and you've got like some sort of labels that you can do gradient descent, and that you can update both the image representation as well as the text representation. Lots of details on how to do this, but this is like on an intuitive hand-wavy level, something that Clip does. So that means that if I were to give Clip an image, I'm able to get the embedding from the image part of the network, but I can also give Clip, if I wanted to, text. So the Clip is one of those models that can do image embedding as well as text embedding. And in my experience so far, it is actually one of the preferable ways to do image embedding in general, even though it's not necessarily trained on anything specific. It just has really good representations. But it also comes with the extra benefit that I could also come up with a text query to compare image embeddings as well, which is definitely kind of a useful feature. That'll be something for a different demo, like a slightly different time. For now, what I just want to focus on is how you can actually build this in a scikit-learn pipeline. So let's do that. So we have a pretty similar setup as what we had before. I have the image loader. We have a similar setup to before, but now we have an extra step. So again, we have an encoder that's happening just before a classifier is happening, so that's good. So we know for sure that this model is getting something numeric. I'm loading the clip encoder from the multi-submodule from Embetter, by the way. These are the multimodal models. And before Clip can do anything with it, I'm just making sure that I've got my image loader. I need to make sure that my images are loaded as Python objects. And Magda, again, should that be a question? If you have a data frame and in the data frame you've got a path, again, you would need to have a column grabber before. But I hope that, as is at least, people understand that this is indeed still a scikit-learn pipeline. Nothing too crazy, nothing new under the sun, so to say. Oh, I forgot to import that. Did I? Yeah, so from Embetter, vision, import image loader. I think I had it there. Yeah, there we go. And again, if I would just have a look at the pipeline, the pipeline looks like a very normal scikit-learn pipeline. These are just scikit-learn components. Okay, so as a, I guess, final demo, I'm doing something very similar to what I did before. I'm still doing the few shots trick. But the images that I've got here are images on disk. So there is a folder here somewhere called animals. And in that folder, I just have lots of photos of animals. So apparently there is a cat breed called Abyssian. It's a very tiger-like feline, so to say. And I've got images of American bulldogs, and I've got this huge list of cats and dogs, so to say. These are all different images. I can give you the link to this file if you'd like. It's on GitHub. But what I can do is something very similar to what I did before. I've got my one example of this one cat. I've got this other example of this one dog. Those are my images. I've got my target variable, like it's a cat or a dog. So lo and behold, we've now trained. Fun fact, by the way, notice how the color in this pipeline is different from the color here. That is because this pipeline hasn't been trained yet. This pipeline has. Like, subtle difference, but like something to keep in mind as you're using a notebook. But then as like a final demo, what I thought would be kind of cute is what I can do is I can just have a look at like the top few images here, and I can just have a look at like, if I just train this system on one cat and one dog, will this be good enough to make like somewhat reasonable predictions? So I'm loading up all these image paths, and for every image path, I'm making a prediction. And then you can see that as I go through all of these animals, most of the time it's saying that it's a cat, and you know, that's totally accurate. There's a few times here when it's saying that it's a dog, which is not necessarily accurate, but I will say, like, you know, not the worst. Like, to a very large extent, it's, you know, mostly cats, so it's pretty accurate. But then apparently there's something about a Bengal. Let's go for that one. Yeah, so this is a different kind of cat, and you can see that it totally has difficulties with it. It still gets cat most of the time, though, but you can just see there's more dogs in there as well. Not the most unreasonable, but apparently there's like a couple of these examples where it's just really confused. And here's kind of the thing. Like, I also would not expect this classifier to be perfect in any way or form. The thing that's interesting here is that this is barely any effort. Like, that's the real thing that I think embeddings give you. You have the same problem with do I love the dog? Do I hate the dog? When is something similar? You have a very familiar conundrum when you're dealing with embeddings and images. But the cool thing that remains is that this is 2 lines of code, really. Like, it's barely a line of code. It's just adding more components to your pipeline. And the reason why I was so excited to build this tool is because it both speaks to the power of scikit-learn, like we can just click stuff together still. But if you're working on an image classification problem, this is just so nice to have around when you're doing rapid prototyping. There's no need to immediately dive into PyTorch. You can just use this to help you get started with either labeling your data, or it might just be the case that, I don't know, given the data that you've already got like 90% accuracy maybe. And who knows, maybe that's good enough. Sometimes there's also a good reason to sort of, yeah, this might sound counterintuitive, but I have been in teams where suppose that PyTorch would be 1% more accurate. That can be a reason to move to PyTorch, but it can also be a reason to stay in scikit-learn, because if you're going to introduce a new software stack to the entire team, you're also going to increase complexity. And like either way could be a good choice, but there's also a trade-off there. And I will argue that part of the positive trade-off here is we can keep using the scikit-learn stack without complicating it further. And there's something I think very valuable about that as well. I guess like a final thing that I do think is maybe fun to mention as well, like if we're talking about embedding images, this is the clip encoder. So this has been trained on text and images. There are also these encoders that have been trained on ImageNet, which are these competitions with like 1,000 classes. There's also another way of encoding that's just a little bit simpler and actually has a few use cases, and that is to just encode the color histogram. Embetter has support for that, but one thing you could just theoretically do is you could look at an image, right? And you could just, let's say, make a histogram. And I'm going to do the fancy thing, and I'll actually use colors for this. You could say something like, okay, but this image, if we have 0 over here, we've got very intense values here. We can go through each pixel and we can check like how RGB, how many green values do you have? You can kind of get like an impression of the green in the image. You can kind of do the same thing for, red. And you can do the same thing for blue, right? And what I could do is I could say, well, okay, those are RGB values. That's all well and good. But then I can go ahead and bucket this, so to say, and then I can just concatenate all those buckets together. So I've got my red values bucketed. I can do the same thing with the green values, and I turn all of that in the flat array. And then I basically have an embedding that just represents the color usage in an image. And there are just a couple of these interesting use cases where that could actually make a bit of sense as a starting point. I've actually had someone tell me that they were doing this like just to get started with satellite imagery. They weren't using Embetter like specifically, they were using different tools. But if you're dealing with satellite imagery and you just want to know like when is there a town and when is there like a field of grass, I mean, color is a pretty good proxy. Like it doesn't necessarily have to be complex. And like if you go to the docs, I think you can find a demo where I do something similar with emojis, where you can just see that all the smiley faces are on one end and like the stuff with more complex colors are on a different edge, etc. But I wanted to maybe mention this also to emphasize that embeddings are also just that. They're just representations of an image. And the fact that a neural network is somewhere in the middle there could be useful, and there could be reasons for it. But the main name of the game is to come up with some sort of representation that's reasonable both in terms of the data going in as well as the label we would like to get out. That's the name of the game here. And the kind of the hope with Embetter is that there's just a couple of these embedding tricks in there that could make your day-to-day just a bit easier. So, end of pitch. I hope this was just kind of useful. I will make sure this notebook is put up online somewhere, and I will make sure that it's linked in the show notes of this episode. Looking at the time, like we're almost at it for an hour now, so it's also good to kind of wrap up. What I will do now, though, is quickly check at some of the questions that come in. Magda is asking if some of this stuff could work for spectrograms, and in particular, I'm assuming that you're thinking about doing stuff with audio. I currently don't have any support for that in this library, but I'm definitely open to it. It's just that I've never really worked on an audio use case before, so it's not my field. I would appreciate it if someone who has a bit more experience, if someone could like tell me what is important. Like, because one thing with spectrograms is there's a time axis, so to say, and there is the frequency axis, and that means that we have a mapping from audio to a two-dimensional representation, which is fine. It's just scikit-learn wants to have one thing, one array, not like a two-dimensional array. The scikit-learn wants to have one-dimensional items per row, or at least the algorithms do that. So I would need a little bit of help to maybe understand how to properly encode that such that the scikit-learn models can actually use it. But if people have ideas, go to GitHub, let me know. I'm definitely open to it. And then I guess like a final question, are multimodal embedding models a better fit for multimodal data than to apply different embedding models? So let's say you want to retrieve movies on poster images and synopsis on embedding similarity. So kind of again here, let's take a step back and just wonder what kind of data sets these embedding models are trained on. So just as an example, like let's say I've got a text model that also has images that's trained on Wikipedia. Let's say that if two sentences are from the same article, we can say that they are similar or not. We can come up with a data set for that. Similarly, we have descriptions of images. We can also do something fun with that. And we do that for all of Wikipedia. Maybe that's a pre-trained model. That's great. However, if I then think of movie posters, are movie posters well represented on Wikipedia, or should I expect more sciencey stuff on Wikipedia? And also in terms of language use, should I expect something that's very formal on Wikipedia? And does that adhere to the slang that you might see on a movie poster, which is usually sort of meant to market towards youths, to sort of... That's my image of movie posters, at least. What I'm getting at here is that, of course, these embedding models are usually trained on a very general data set, and that's great. That makes it very general to apply. But more often than not, at some point you're going to hit this thing that your use case is specific. And it will be very strange if we can come up with something that's super general, that at the same time is also able to deal with every specific use case out there. There's usually a need for fine-tuning or customizing it to some extent. At least that's the case in my experience. So back when I worked at Explosion, we did a bunch of experiments with OpenAI as well. And also there, we just saw that even though OpenAI is very compelling, and those large language models are very compelling, they are usually trained for a very general use case. And if you are doing something with text that's very specific, there comes this point after like 2,000 labels or so where custom models trained from scratch do perform just a little bit better. I don't know if this is true for every use case out there or for every domain, but it's a somewhat general pattern that we've seen internally. And it's also something that seems to be confirmed by some academic research as well. So just keep it in your mind as well that like embeddings are very powerful, but they are like general. And you probably want to have something specific eventually because you have a specific use case. This phenomenon also makes it super hard to train these embeddings. Like what data set do you pick and why and for what use case? And collecting these embedding data sets, are there no mistakes in the labels? There's lots of stuff that like I would love to train my own embeddings. But I have no reason to believe that I can do it better than some of the embedding models that are out there right now. Like it's the more I think about training my own embedding models, the more that I respect how hard of a problem it actually is. You need so much data. You need to babysit the model. It's a huge endeavor. So I'm personally quite thankful that there are good open source projects. In particular, actually, I do want to give a small shout out to that, partially because I know the maintainer. So all of the embedding models that I've shown you so far are based on a library called sentence transformers. There we go. You can go to the documentation directly. This is also a pretty easy library to use directly. Theoretically, if you just want to do embedding stuff without scikit-learn, you can also use this library directly. The main thing that Embetter does is it offers support for this library and others to play nice with the scikit-learn pipeline. That's something that sentence transformers doesn't do out of the box. But it is a really cool library, and it's really cool to see, like recently a new maintainer stepped in, and it's just cool to see somewhat more recent research actually being made available in this tool as well. So there's definitely like more quantization stuff that you can do under the hood. There are these things called Matrushka embeddings that they do a fun trick here. I will say, like that the Matrushka idea is actually a funny one. But this is a solid package. Like this is what I use under the hood for most of my Embetter stuff, and I've been a very happy user so far. So definitely just check out this doc as well if you're interested. It's a cool library. Cool. So I guess that's the end of the live stream. Kind of. I will leave it open for like quick questions, and I'll be on the chat and stuff. But this will also be a good time for people to go back, like return from their lunch break and all of that. If you're in the Netherlands, like me. I hope you have a fun, long weekend. And if not, thanks for joining. Reach out to me on social media if you want to have a topic being discussed here. So I actually got reached out to from a couple of folks who wanted me to do embedding stuff. So that's what I'm doing today. If there is another topic that you feel is underrepresented or deserves some more attention, definitely let me know because we can do more stuff in these live streams. Yeah, so there's a final question that comes in. If I've ever worked with astrophysics data, the answer is no. I've never really done anything with astrophysics. I'm not an astrophysicist, and I'm sure there's very interesting stuff there. But I'm more of an industry person than doing things with astrophysics. That said, I would definitely be open to seeing a talk from an astrophysicist talking about embeddings for astrophysics use cases. I do think that could be like really fun. Not my domain though. But anyway, good. I think this has been going on long enough. Everyone, thanks for joining, as always. And yeah, I'll try to be back next week. Let me know if there's topics that are missing. Y'all have a good one.